Now let's discuss some observational implications of the special relativity dictionary. Okay, and clearly these observational implications will become important as the speed of these frames relative to each other becomes comparable to the speed of light. So the first implication comes from the equation or the dictionary from the transformation of time. So we saw that Ct prime is 1 over square root 1 minus v squared by c squared Ct minus Vx by c. Or let me just erase this and let's go back to the original equation that we had written down in terms of t rather than Ct. Now, what does this tell us? Okay, so imagine that you're in a frame S. So it's like you're standing on that railway platform and you are one observer O over here, and you have a bunch of friends who are separated from you by fixed distances of 1 meter, say. So you have all these friends, and now a train goes past you, and that's in frame S prime. And at any instant of time in your frame, there's a well-defined instant of time where all of you have the same value of time on your clocks. But as we've seen before, this well-defined instant of time is not the same instant of time as seen by observers on the train. So if I look at observers on the train, and if we were to look into their clocks, the clock readings on each of their clocks would not show the same value. Okay, because the instant t is equal to 0 here and the instant t is equal to 0 here, which can be attributed to the events of, let's say, observer O and O prime meeting each other, and friend 3 and friend 3 prime meeting each other, the event O and O prime meeting each other is not simultaneous with the event friend 3 and friend 3 prime meeting each other as seen by observers on the train. They are simultaneous as seen by the ground observer, but not simultaneous as seen by the train observer. How do we see this from the Dictionary of Special Relativity? Well, the Dictionary of Special Relativity tells us that the location x is equal to 0, t is equal to 0, which is where O is located, is the same as the location where t prime is 0 and x prime is 0. Okay, that is where O prime is located. So t prime would be 0 here. But if we ask what happens to the time on the clock that friend 3 prime sees when he comes face to face with the friend f3 sitting on the platform, well, what we would see is from the Dictionary of Special Relativity, this t would be 0, okay, but x would be plus 3. So therefore this time would be negative. Okay, that is, this time would occur earlier according to the train observers compared to the event of O meeting O prime. So in other words, friend 3 prime would appear to meet friend 3 before O prime met O, or before they came face to face. And similarly, if I look at friends to the right, let's call these friends 4, 5, and 6. Friend 6 would appear to have a positive time on their clock when they come face to face with friend 6 on the ground. Okay. So that means that they would meet friends, according to the train observers, friend 6 prime meets friend 6 prime, friend 6 later than when O prime meets O. Okay. So if the observers on the ground look into the train and just read the times on the clocks of these friends, they would see clocks which appear to be out of sync with each other. Okay, so the clocks on the train appear to be out of synchronization as seen by a ground observer, or as seen by the ground observer. Okay, so clocks on the train, that is in the frame S prime, as seen by the ground observer in the frame S. All right, and not only do they appear to be out of sync, the synchronization grows worse as you move further to the right or you move further to the left. Okay, so these clocks look like they are showing more and more negative times. Okay, so synchronization appears, or synchronization difference appears to be worse further away from the origin. And secondly, and the last point is that the synchronization, or the clocks on the train, appear to be negative, that is to say that they are behind, or appear to be running behind, as we go to the or as we go along the direction of motion of the train, and they appear to be running, or they appear to be offset ahead. Sorry, running ahead is, running behind is the wrong word, as we shall see. There should be offset behind versus offset ahead as we go opposite to the direction of motion of the train. Okay, so the clocks over here appear to be showing times earlier than t is equal to 0, and more and more early as you keep going to the right. And the clocks to the left appear to be showing times later than t prime is 0, and further, more and more later as you go further to the left. Now, what about the rate at which these clocks tick? Okay, so this only tells us at an instant of time, t is equal to 0, as seen by the ground observers, that the clocks on the train appear to be out of sync. But what is the rate at which the clocks on the train appear to tick? Well, that is a different question. So the first thing that we saw is moving clocks appear to be out of sync. But now we can ask a second question, which is, what is the rate at which the moving clocks tick as seen by the ground observer? Remember, according to the train observer, nothing unusual is going on, right? Their clocks are all in sync with each other, okay? And their clocks are ticking at exactly the same rate as they would expect. They don't see anything strange about the rate at which their clocks are ticking. It's only when you make a translation to the ground observer and the ground observer is trying to interpret what the train observer is seeing that you run into these strange things. So we already derived for example, the relationship between the time on O prime's clock, that is an observer sitting at x prime is equal to 0, as they go on moving to the right, what would happen to their clock compared to the time shown on O's clock? Okay, that is the time shown on O's clock, which is initially at t is equal to 0. So we had showed that t is equal to 1 over square root of 1 minus v squared by c squared t prime, which we can write as so this is the time on the moving clock. This is the time on the ground clock. Okay. And this is moving clock moving with a particular observer on the train. So the way to think about this is, imagine that O prime is moving to the right. And now as they're moving to the right, as they pass these different friends, the friends look in and see what time O prime's clock shows them. And they report that value of the time, which is t prime over here. Okay, and since all the ground observers have synchronized clocks, they can tell you the time at which they passed O prime, and that would also be the value on O's clock as well. Okay, and that would be the time t. So this would be the time that had ticked on O prime's clock. This would be the time that has ticked on any of the ground observers' clock, since they're all synchronized. But we can say in particular on O's clock. And this factor here is just gamma, or our boost factor. Okay? So what this tells us is t prime is equal to t divided by gamma. Okay, and we saw that in the or for speeds much less than the speed of light, gamma is just close to 1, and in that limit t prime would be t. Okay, that is, you recover the ideas of Galilean relativity, where all clocks just appear to tick at the same rate. However, what you can see is, now if I ask about a time interval as seen by the ground observer, which is some fixed value of t, would yield a value of t prime which is smaller. Okay, so a fixed time interval on the ground would result in t prime which is smaller by a factor of 1 over gamma. Now if you remember what gamma looks like, gamma as a function of v Okay, as v gets close to the speed of light, okay, it just shoots up rapidly. Okay, it starts from 1 and shoots up rapidly. So what this tells us is that as speeds get close to the speed of light, okay, the time interval that passes on the train appears to be smaller and smaller compared to the time interval that has passed on the ground. Okay, so in other words, moving clocks appear to tick more slowly than clocks on the ground. Okay, this same relationship between the time intervals, let's call this delta t prime and let's call this delta t. This same relationship between the elapsed time intervals should be true for any observer on the train. So if I take any clock and ask on the train and ask how much time has elapsed on this clock after a time delta t has elapsed on the ground, that moving clock would appear to tick slower. Okay, and this relationship must be true because no observer on the train is special, right? So all their clocks must appear to tick at exactly the same rate relative to clocks on the ground. Okay, so the clocks on the train appear to have a phase offset relative to each other, and they all appear to tick in sync relative to the clocks on the ground, but they tick at a slower rate than the clocks on the ground.